Okay, good morning, everyone. Apparently, I hope you can hear me now. I'm very excited to have been invited to give you this keynote. For 3 years, just sent videos because it's 3:30 a.m. here. I live in France, near Paris. And this year I decided, okay, I need to do better and to be live with you. So we're going to talk about the new things between, well, some of the new things between the JDK 21 and the JDK 25. I was introduced, and because we're live, one thing which is better than compared to when you're just watching a video is that you can actually ask questions. So if you ask questions on the Slack channel of the conference, I'm on it, and I will be able to monitor the question while I'm speaking to you, and answer them if you have any. So please just send your questions, and I gladly ask them as soon as I can. So my name is Jose. I work at the Java Platform Group team at Oracle as a Java developer advocate. I publish many links on the internet, so please just follow the QR code to get videos and labs on my GitHub channel, on my GitHub account, and different things. I also contribute to the dev.java website, and we just announced a few days ago, before the release of Java 25, the fact that there will be another Java 1 this year in March in San Francisco, Java 1 2026. And if you're interested in everything Java, you should definitely follow the announcement and whatever is happening in this conference, in case you cannot make it yourself, of course, because attending is probably better. We publish a lot. We publish a lot of content with the developer advocate team. We are about a dozen of us doing that. You can connect to different social medias, including YouTube. We're doing also podcasts and kind of blog articles on the dev.java website. And we just finished the publication of a series on called The Road to 25 to help you migrate your application between the 21 and 25, in case this is what you need. And I would like also to advertise the openjdk.org website, because this is where everything is happening. All the documentation and all the projects I'm going to talk to you in a few minutes are actually hosted on the OpenJDK website. All the mailing lists where you can give feedback and get information are there. So this is definitely the place where you should go to if you really are interested in all this. And if you want to download, excuse me, early access versions or preview versions to check the features you're most interested in, you can also connect to jdkjava.net, where you can download all the versions that you want. The JDK 25 has just been released at the beginning of this week, so it's now ready for use as a generally available release. But you can already download the early access version of the JDK 26 in case you really want to be on the edge of things. And you can also download early access versions of Loom and Valhalla if you want to test things, and we're going to talk a little more, especially about Loom. So why is this 25 version interesting? Because people call it an LTS version. Now, I would like to spend a few minutes talking about this kind of LTS version, because LTS version is not a JDK notion, right? There is no such things as LTS versions on the OpenJDK website. If you check all the versions since the version 11, here you have between 11 and 16, and here you have between 17, which was supposedly an LTS, 11 was also supposedly an LTS, to 22. You can see that actually every version is released first as a GA version, and then there is a first level of patch, then the second level of patch, and then we switch to the next version and do that again. And you see that you don't have any difference between 11, 17, 21 is here, sorry, 21 is also here, excuse me, between these so-called LTS version and other so-called non-LTS version. From the OpenJDK project, from the JDK that you can download on the OpenJDK website, there is no difference between them, okay? And you can see that 23, 24 got exactly the same attention and the same release train as 25 that was just released at the beginning of the week. So you can actually download any of these versions and use it in your production environment for free. Okay. The fact that there's no difference has a consequence. It means that 24 version is not some kind of pre-version, beta version of the 25 version. It really has the same status, goes through the same quality control process, and is as solid for production as 25. These LTS versions are really a vendor notion. Okay, some vendors, and there are something like 20 of them, actually provide long-term support for this specific version, 11, 17, 21, 25. Some of them are free, some of them are not. That's another matter. The licenses are different, but this isn't a vendor concept. It is not an OpenJDK concept. All the versions are the same, and you can use them in your production environment without any problem. If you want to deep dive in what is driving actually the design of the Java platform, you definitely want to watch this keynote that was given by Mark Reinold in 2025, in March 2025. I just put a QR code here that will take you to the exact time code where it describes all this, described in 11 points here, 11 points. What is making, what is driving, what is motivating everything that is released in Java, in the JDK. So if you, moving on, these are the JEPs that were released between 17 and 21. So we have 4 versions, and that was 23 JEPs. And if we do the same between 22 and 25, we have 66 JEPs, which is a lot. So we're not going to see all of them one by one. That would take way too much time, probably more than the day, actually. I would just like to focus on some of them. And all these JEPs, you can actually, the specific JEPs, you can find them on this page of the OpenJDK. I put in yellow all the JEPs that you're not going to use in your application because they are either preview features or incubator features. So you can test them. You can play with them on side projects to see what the patterns of code they are giving you and the features they are giving you. Essentially to provide feedback and to post the feedbacks on the corresponding mailing lists, but you cannot use them in production. What you can use in production is the rest, so it's all these ones. In green, you have the ones that are about APIs, and you can see that most of them are about APIs, and you have many aspects of the different APIs available in the JDK. And the blue one, because there's only one actually, is a language feature that was released in the JDK 22, and it's the capacity that you have to put an underscore to say that the given variable will not be used in your code. The purple and the red one are about different aspects of the JVM. So they're not going to impact the way you write your code or your way you organize your application. For instance, ahead of time, command line ergonomics is not going to be useful for you if you write your code. Okay, so I'm going to focus on just some of them. So I checked what I talked about last year to avoid repeating myself year after year. So I would like to do that in this order, and if time permits, we'll move on to the stable API. Start with the gather API, which is an addition to the stream API. I guess you're all using streams in your application, so playing with the gather API is something that you're probably going to do very soon if you're on 25. The Gather API was actually released in the 24, so already 6 months ago. And Loom also got some attention. There was an issue on the pinning of also thread on Platinum threads, the in synchronization block that has been fixed. The class loading pinning issue is also currently being fixed. It's not fixed yet, but people are working on it. We have a fifth preview feature of the structured concurrency API that we are going to talk about. And the scope value API, which is a replacement for thread locals, is released as a final feature in the JDK 25. I also give you a glimpse on what is coming for structured concurrency in a JDK 26, because we already have that. Maybe it's not fully done yet, but we already have a good idea of what the structured concurrency API will look like in 26, and it will still be a preview feature. That's the plan. If we have the time, we'll talk about stable value, which is a preview API and really great. Has to do with the way you can create your constants in your application. And we'll also talk about, I guess we won't have time for that, but okay, never mind. Amber, Panama, and Valhalla. Many people are making fun of Valhalla. We are going to retire. We are going to be out of business before Valhalla makes it as a final feature. Actually, Valhalla is quite close to deliver the value types feature. And we also, if we have the time, we'll also talk about that. And if you have questions, specific questions on these features, please send them to the Slack channel, and I can just show you things about that. Okay, so let us start with gatherers. Gatherers are covered in a JEP 485. I don't know if you're used to reading JEPs, but if you don't, I really encourage you to do that, because JEPs are really meant to be educational documents. They are not specification documents. You have why has this feature been added to the JDK? Why has it been designed in the way it has been designed? You have examples of code, you have patterns, anti-patterns, and these kind of things. So reading JEPs is actually something that is extremely useful when you want to learn about features. I would like also to advertise a page I added to the Java website, specifically on the Gather API, with many examples that you can run directly from within your browser. You see, this is a screen capture of your browser. If you hit the run button, it will just execute the code that you have in this little window without having to install anything on your machine. I guess you all have a JDK on your machine, but you can still do that. And if you want to go further, you can also follow this link to this video that has been made, to this presentation, sorry, that has been made by Victor Klang on the stream gatherers. And Victor Klang is the person who actually designed the API and wrote it. So it's a final feature of the JDK 24, sorry. So we had it 6 months ago. How is it working? A gatherer is actually a way to create your own intermediate operations in the Stream API. We've been playing with the collector API since the beginning of the Stream API, actually. And the collector API is a way to create your own terminal operation. But there was no way to create your own intermediate operation. And this is the gatherer. This is what the gatherer is doing. The gatherer is an interface, technically speaking. There are actually other interfaces, but the gather interface is the entry point of the API. There is a method gather on the Stream API that takes a gatherer as a parameter, and that returns another stream, of course, because it's an intermediate method. And you got a factory class, gatherers, which is much simpler than the collectors factory class. You have something like 40 or 50 methods in the collectors API. In the gatherers API, you have only 5 or 6. I can't remember exactly. And then this is the simplest pattern you can use. You have an upstream that could be just a stream you created on a list, for instance, or something more complex than that. You create a gatherer, and then you gather this upstream, passing this gatherer as an argument, and you get a stream of R. If you compare this pattern with the collector pattern, you can see that actually it's a little different. The parameters of the gather interface are the same as the parameters of the collector interface, T, question mark, and R, but the result is not exactly the same. A collector will return an object of type R, so R is the type of is the return type of the collect method, whereas the R type is the return type of the stream returned by the gather method. Okay, so in one case it's the stream of R, and the other one is it's R. So the status of these parameters is not exactly the same. Technically speaking, this gather interface is actually a functional interface. So a gatherer is a supplier of integrator, and you need to be careful because the order of the parameters is not the same in the integrator interface as in the gather interface. There is an inversion between the A and the T. And the integrator interface is itself also a functional interface. It has a single abstract method that takes three elements: a state, an element from the upstream, and a downstream, which is a model of the downstream your gatherer is going to push elements to. Now, this downstream is also an interface, of course. It has nothing to do with the stream interface. It does not extend it, does not implement it whatsoever. It's really a completely different interface. So how can you write a gatherer? Well, this is the simplest gatherer that you can write. Let me go back one slide. You can see that this integrate method from the integrator interface returns a Boolean, whereas the integrator returns an integrator, of course. So this is a way of pushing an element to a downstream without doing anything. You take your gatherer, you use the factory method off, and actually this factory method takes an integrator. So all you need to give to this off method is an implementation of the integrator, right? So you have the three elements, the state, and since in this Lambda we are not using the state, we can use this feature, this language feature I talked to you about a minute ago, which is the underscore. So underscore means that you are not going to use this argument. Then the element, which is coming from the upstream, and the downstream, and all you can do is just push this element to the downstream by using downstream.push, and this push method returns a Boolean, so you can just return this Boolean, and the compiler is happy, and this gatherer will work. You can use it in the stream. It doesn't do anything, just it's a transparent gatherer, but it's the simplest gatherer you can imagine and that you can use. If you want to do a mapping, then you can transform your elements, and then you can map your element using a mapper, okay, in that way, and then again returning downstream.push. Now, if you want to do a filtering, now you come across something that you don't have to do with the mapping, which is, okay, if your element doesn't pass the test, okay, you call filter.test, and if it's false, if it's true, okay, you push it and you just return the corresponding Boolean. But if it doesn't pass the test, then you have a problem because you can't return the Boolean that you just got from the calling push, right? You need to invent the Boolean you need to pass. As a rule of thumb, when you're using gatherers and you don't know what Boolean you should be returning, return true. Do not return false. Returning false doesn't do the same as returning true, and return true is always your best bet. It may be suboptimal, but that's the best choice you can have when you're really lost and you don't know what to do. When you push things to a downstream, there are several rules that you need to understand and to follow. First, you can push as many elements you want to a downstream. You can even push 0 elements if you want. If I go back one slide, you see that if the element doesn't pass the test, the filter, then you return true without pushing anything, which is okay. You can totally do that. And second, if you call a push, then it returns a Boolean. And the semantic behind this Boolean is the following. If it returns true, it means that this downstream accepts more elements. So if you push more elements to the downstream, this downstream will actually use these elements. And if it returns false, it means that it does not accept any more elements. And that if you carry on pushing elements to it, then you are not going, these elements are not going to be taken into account. Think about a downstream that could be a call to another intermediate operation that would be a limit, for instance, and you have a limit 5, okay? So for the first 5 elements that you push, the downstream will return true 5 times, and then starting with the 6th element, it will return false because it's a limit 5 and it will not do anything with these elements. But if you keep pushing, that's okay. You won't get any exception. So you can do that. This is why I tell you that if you return true, you're not really making any mistake. Okay. And your own integrator should also follow this rule. That means that if you return true, you're telling your upstream that yes, you will do something with the elements, it will push you. And if you return false, it means that you are not going to do anything. So if your upstream is correctly written, so if it's an intermediate method of the stream API, for instance, then as soon as you return false, your gatherer will not be called anymore because the stream implementation knows that, and it will not push anything to your integrator anymore. But if yourself you are pushing to a rejecting downstream, that is a downstream that returns false to you, then you will not have any exception. It's just suboptimal to do that, so you should avoid doing that as much as you can, right? So it means that your downstream is actually managing an internal state, which is, by the way, mutable, and which is called rejecting. And there is an isRejecting method on the downstream interface, which is a default method. So yes, this downstream interface is also, a functional interface. So this rejecting state follows a certain number of rules that I think it's good to know them. The first one is that it always starts with false. So you can see a downstream as a door, and when you get a new downstream, a fresh downstream, this door will always be open, okay? So when you get a fresh downstream, you can always push at least one element to it. It cannot commute from false to true. So once this door has been closed, it cannot be opened again. And this is why when you got false, you can just interrupt the stream. No more element is going to be processed. And this one, I put it in light gray. It can only commute on a call to push. Now, this is not part of the specification, but all the downstreams you can get as of now from the JDK are following this rule. That is, if you don't call push, the door does not close on itself. Now, you could create your own downstream that could commute on a clock, for instance, that is on some external information from your stream. And so creating a downstream that does not follow this third rule. But if you do that, then you know what you're doing, your application knows what you're doing, and you should write your gatherers accordingly. But if you don't do it, then you can safely assume that this rule number 3 holds. And I don't know for you, but every time I hear about internal mutable state of object, the first question that comes to my mind is the downstream a thread safe object? Okay, internal mutable state, if you have multiple threads, then you can be in trouble. And the answer is simple, no, the downstream is not a thread safe object. Okay, so don't bother calling, don't try to call downstream for different threads. Now you may be thinking, but how could I call the downstream object from within Lambda using different threads? Well, it turns out that a stream can be a parallel stream, and that different threads, if you are in a parallel stream, can indeed call your downstream object. Okay, and we'll talk more about that in a minute. So you may be thinking that when you write an integrator, and this is an integrator, checking for the rejecting state of this downstream may be an optimization. Okay, I first check if the downstream is rejecting or not, and if it's not rejecting, then I can carry on with my computation. Is it really an optimization? Let us think about that for a minute. When you first call this method, okay, this is a fresh downstream that didn't got any object yet. And you know from rule number 1 that this downstream is an open door. So this is rejecting call check will be false, and you are not going to return false, you are going to return downstream.push at once. Now, once you get, because you're returning the Boolean correctly, you have two solutions. Either this Boolean is true, okay, or it's false. If it is true, it means that this integrator will be called again with another element. But because in the meantime, no call to push has been issued, the rejecting state could not commute. So this downstream is rejecting is still false, and you're not going to return false at this point. You are going to carry on returning downstream.push. And if this downstream.push is false, then because you returned false, okay, your integrator is not going to be called anymore. The gatherer will not going to be called anymore by the stream API because you told the stream API, the upstream, I'm not going to get any more elements, so you can stop there. So actually, if you write this code in an integrator, this downstream is rejecting will always be false. So don't bother putting this kind of code in an integrator. It's totally useless, and it's certainly not an optimization. It's just a piece of code that is useless. This is in an integrator. We're going to see in a minute that you can actually call this in other places. So a gatherer can also call an internal mutable state, which is the first element of this integrator. And this state is initialized with an initializer. And once you have one state, this state would be the same. Your gatherer will always be called with the same state. So if you want to create a limit gatherer, you can create a counter class wrapping a counter. You initialize with counter column new, and then you write your downstream element, your integrator in that way. You increment count, check if it's lesser than limit, and push if that's the case. And if it's not the case because you've reached the limit, instead of returning true and saying the upstream, hey, you can keep sending me elements, you are going to return false, telling your stream that you're done with that. You could do the same with a distinct gatherer, okay? And here I'm going to create a new hash set. This is my internal mutable state. And then I add elements to this hash set. If this element was added to the set, meaning that it was not there yet, I can push it to the downstream. And if it's not the case, this time I need to return true, telling the upstream, hey, you can send me more elements. It's not because I didn't push the current element that you can't keep sending me element. And you can do the same with the sorting gatherer. So this time it should really be a tree set and not a hash set. Okay, but this time, sorry, so there's a mistake in the slide. But this time you need to be careful because you need to push elements that have been sorted, right? So you can check if this element is added. You add your element to the tree set. You return true because you want to see the next element, but then you haven't pushed anything. And at the end of the day, you have a tree set that is full of elements, but you can't push them. You can't push them because your integrator is not called anymore when you don't have any element. And the first element needs to be the smallest one, right? So you cannot push anything until you've seen all the elements of the upstream. So for that, you need another element in this gather API, which is called a finisher. And by the way, if you know the collector API, you also have a finisher in the collector API. Okay, this finisher is called when you don't have any more elements coming from the upstream. All right, so it does not. It's the same as an integrator, technically speaking, but it does not take an element because there's no more element to be pushed. It only takes the set and the downstream. You can push all the elements from this tree set to the downstream using an all match. All match will check every time you push if push is true and will carry on. Is that the case? And it does not need to return true because once this finisher is called, there is nothing to be done after that. You don't have any more elements to push. So technically speaking, so far a gatherer is built on 3 elements: an initializer, an integrator, and a finisher. And you absolutely need these 3 elements in this case. When you are in the finisher, you can call downstream. You can call downstream is rejecting for one reason, which is the following: a finisher is always called after an integrator has been called, but maybe in the integrator, because you called push in your integrator, the rejecting state switched, and the door is closed. Now, if you think that creating a stream on a tree set is an overhead that you do not want to pay, then calling is rejecting indeed can be useful, and it can be useful in other cases. So calling is rejecting is something you may consider in a finisher. It is useless in an integrator. I would like to finish on this part on gatherers by just talking a few minutes about parallel gatherers, because I sneakily used, let me go back a few slides, the off sequential method instead of the off method without telling you. Okay, gatherers support parallel stream, of course, but a gatherer itself can be a parallel or a sequential gatherer, but both of them can be used in parallel streams. Why? How is it working? It has to do with the state. I told you that there is only one state object for a gatherer. Actually, there is one state object per thread for a gatherer. So your integrator will get an element and the current state and will mutate that state, and this mutation will be seen by the next element. But if you're in a parallel stream, the gatherer interface implementation actually creates one state object per thread of your common function pool. So in the end, you end up with 4 different instances of this state object, and you need a combiner to combine them. So the parallel distinct gatherer creates an hash set, pushes element to this hash set. Now it cannot push them again anymore directly to the downstream, because since you have 4 different instances of state, you may have an element that has already been seen, but which is in another instance of this hash set. It has to play with a combiner, because once all the elements have been pushed to different hash sets in different threads, you need to combine these different hash sets, and then you push the resulting hash set directly to the downstream. So you have another element in this parallel distinct gatherer, which is the combiner. So sequential gatherers cannot be called in different threads at the same time, and they are sequential because you cannot create, or you did not bother creating, a combiner for them. So if you don't have a combiner, you cannot have different instances of your state object, because you cannot combine them in the end. But you can still use them in parallel streams. And this is how it's going to work. You have your source, you are in a parallel stream, so the substream will be processed in the different threads of your common function pool. Then you have your sequential gatherer that will collect all these streams all together and process them in a single thread. Okay, and then it will push to the downstream that can itself be a parallel stream once again. So this is the data flow of sequential gatherers used in a parallel stream, and this is new from the API. Okay, this was not possible beforehand. So a gatherer, an initializer, an integrator, a combiner, and a finisher. I didn't talk about greedy integrators. Greedy integrators are integrators that cannot interrupt the stream in themselves. So an integrator either always return true or always return the result of downstream push. And you can decide to work in parallel or not for them. A sequential gatherer can work in a parallel stream, and a sequential stream can compute mappings in parallel. So you can do both. You can do that with the gatherers factory class. So gatherers are final in the JDK 24, sorry. So they are still final in JDK 25. So you can safely use them in your application. I would like to spend a few minutes on the Loom project. If you have questions, let me check if there are questions on the Slack channel. Okay, I can't see any questions. Please ask questions if you have them, because I have the Slack channel on the side on my phone that I can check while speaking to you. So Loom is about virtual threads. Yeah, sorry. Oh, I heard something. Oh, that was maybe a glitch. So the goal of the project Loom is to bring virtual threads to the Java platform, and this was done in the JDK 21. There was still an issue in the JDK 21 with the pinning on synchronization. If you don't know what it is, doesn't matter. If you know what it is, just so you know, it was fixed in the JDK 24. It also brought scope values, and scope values are here to replace thread locals. thread locals are still there and they are compatible with virtual threads, but you should definitely stop using thread locals in favor of scope values, which is now a final feature, so you can use them in your application. And it will also bring structured concurrency to the Java platform. Now, just to do a quick browse of things on the Loom project, the Loom project aims to fix the 3 issues that this code has, a code that is written with an executor service pattern. Okay. The first issue is that it blocks threads, and blocking threads, a platform thread is bad because a platform thread is an expensive resource and you should try not to block them. The second issue is that it can lead to a loose thread, and you need to fix that. It's a sneaky bug, actually, but you can see that if f1.get throws an exception, like a timeout exception, because the read images service never give you any response, then it turns out that f2.get is never called. So if read links never provide any response, it will consume a thread of your executor service forever. And this executor service that you finely tuned to 16 threads is now working on 15 threads instead of 16. Okay, and it's super hard to detect this kind of problem in your application. What you will see over time is that your executor service will work on 16, 15, 14, 9, 8 threads, and you don't know why. And you reboot your application, and now it's working again. And after one more week, you are working on 7 threads again, and you don't. And there's no way you can fix this code. It's actually super hard. And the third problem is that the stack tracers you get are totally meaningless. Okay, if you have something wrong that is happening in read image, the stack trace you get is this one, and if you check, it takes you on the call to get, but it does not take you on the call to read image, which is actually where you would like this stack trace to take you, and it doesn't do that. So there are 3 things to fix in concurrency in Java. First thing, blocking a platform thread is bad. Second thing, you want to have relevant stack tracers. And third thing, you want to get rid of these loose threads. Okay, so why is it wrong to block a platform thread? It's wrong because the thread is actually a very expensive resource. Okay, it takes about a millisecond to start. You need to allocate a stack for this piece of memory that is the stack of this thread, and most of the OSs are allocating 2 megabytes upfront. So you can actually have only several thousand of such platform thread in an application, and sometimes there are hard limits set by your operating system that will prevent you from having more than something like 4,000 threads. So it means that if you want to write your code with this 1 network request per thread model, you're limiting actually to 4 concurrent requests, which is very bad, because if you consider that a request takes about 1 microsecond of CPU time, your CPU should be able to manage something like 1 million connection, and you're limited to just several thousand. So this model actually was dead about 20 years ago when Java 5 was released. Well, less than that, but yeah, almost. And you need to revive it. So what are the solutions so far? The first solution is the reactive programming solution. That is, 1 platform thread can handle many requests. And if you want to handle 1 million requests, which is what your CPU should be able to do, and you can have 1,000 threads, it means that each thread should be able to handle 1,000 requests per platform thread. And if you have a system where everything is managed by just 1 platform thread, it means that this platform thread should be able to manage 1 million requests per second. And this leads to this kind of code, which is a callback-based async approach. This is written with the completable future API. You have other APIs to do that, but the code is roughly the same, which is both hard to read, hard to write, kind of ugly. And that gives you whole stack tracers, even worse than the executor service pattern. This is the stack trace if you have a problem in read images. Okay, this stack trace doesn't take you anywhere in your code. It's just a disaster. And if you check the cause, it just takes you, hey, yes, some service on line 12 crashed, but you don't know where it was called from in your application. So you're completely clueless to fix this bug. So asynchronous programming is efficient. There's no doubt about that. But the programming model is absolutely horrible, and it's impossible to debug, impossible to refine, and it's on you to write non-blocking Lambda, because async programming is based on Lambdas. All right, so if you go back one slide and say how many, that was the first solution. There's actually a second solution that has been known for years, which is to build a model of thread that is lighter than a platform thread. And how much lighter? Well, about 1,000 times lighter. Okay, it's the same ratio as the platform thread. But being light is not enough. Okay, and this is what was used to design virtual thread. You also want to make debugging possible, and you also want to make profiling possible. Okay. And indeed, this model of platform of virtual thread is actually a light model of platform thread. A virtual thread is just a regular Java object. You can have as many virtual threads in an application as you have strings of characters. Just think about that. All right. And the trick is that blocking a virtual thread does not block the underlying platform thread, even in synchronized block, because now the synchronized stuff has been fixed. On the stack trace side, if something goes wrong, okay, so this is a way of using virtual thread using the executor service called new virtual thread per task executor. Actually, the stack trace takes you where the read image was called. So the stack traces of virtual thread have been finely tuned and created so that it will take you in your application exactly where you want to fix your bug. The loose thread part is fixed by structured concurrency. So this is the new pattern for structured concurrency. You have a structured task scope that you can open. The previous version, you had to do new structured task scope. Structured task scope is now a sealed interface, so you can only get instances of it by using this open factory method. You fork callables to this structured task scope. You need to call join at some point, and join will block until your callables are done executing. And once you have that, you can just analyze the result you have, compose your result here in a page. These subtask objects, you can think about them as future objects. It's a little different than future objects, but it's from a functional point of view, it's almost the same. Okay. And if something goes wrong here, a good read image method is crashing again, well, the stack trace will take you exactly where your structured task scope object actually got this Lambda expression. So it takes you within the Lambda, and it takes you also where you submitted this Lambda to your structured task scope. So now you're fully equipped to properly debug your application. You have all the information you need. I don't know if you remember the previous version of the structured task scope class, but to create your own strategies, you would use extensions of the structured task scope class. That was a class in the previous version. Now this is a sealed interface, and to choose the strategy you want, you need to pass a joiner object. And this joiner is actually the object that is going to carry the strategy you want to apply to analyze the responses of your callables. So this joiner is any successful throw. Okay, so if you have a result, you get it. If you don't have any result, you will get an exception. This one is await all. Await all will wait for all your subtask to here. There's only one, but you could have as many as you need. All the subtasks you get, and it will get the results and the exception in separated lists. By the way, you can analyze your subtask object using this pattern. You also have a joiner that is actually a predicate. And if this predicate at some point returns false, it will actually cancel the scope that it is in, because from within the scope, you can cancel the scope. And the nice thing is that, let me go back one slide, is that this scope object is actually an auto-closable object. So it means that when you exit this try with resources statement, all the threads that this scope object created are going to be cleaned up for you by the API. So this is how structured concurrency solves the problem of loose threads. The problem is that an executor service, you never close it. It is auto-closable, but you close it when you close your application. Why? Because you have platform threads in it, and platform threads are expensive. Structured task scope only creates virtual threads that are inexpensive, so it can create virtual thread on demand and kill them once it is done. Okay, and you can also pass along with this joiner a configuration object, and this configuration object accepts a timeout. And this timeout is actually one of the new features we will have in the JDK 26 that is in March, which is I don't think it has been merged in the main JDK 26 branch yet, but you can see that on the Loom early access branch. So the joiner is itself an interface with the 4 methods: onFork, onComplete, and result. These are the 3 methods that you have in the JDK 25, and in the JDK 26, you will have a 4th method, which is the onTimeout method. So if we now check the concurrency landscape with Loom, the problem of blocking a platform thread, which was bad, is actually solved by the fact that you can block a virtual thread and it is free. Actually, this I don't know if you remember this mechanism of moving the stack of the virtual thread to the heap memory, freeing the platform thread to do something else, makes it so that blocking a virtual thread does not block the underlying platform thread, which is exactly what you want. The issue of having non-relevant stack trace is also solved. I showed you the stack trace of virtual thread, and now you can see that you have stack tracer that you can actually use to debug, which is the first role, what should be the first role of stack trace. And the problem of loose threads is also fixed using structured concurrency. Now, very quickly, I'll take you through the scope values. Scope values is a very super simple API. You just create a scope value with new instance, and it's, let me call it key, and you bind this scope value to a value for the context of a method call, which could be a runnable or a callable. And by the way, you can chain them if you want. And this binding is only seen within the scope of this method. Now, to analyze the scope value, you can just check if this scope value is bound, and if that's the case, you call get. And now the question, if I go back one slide, the question is, what if this method, this runnable that you pass to the run method, what if these methods are themselves creating threads, right? That could escape the scope of this method call, this runnable. Well, if the thread you create can escape, then the binding will not transmit it to the escape, to this scope, okay, to this thread. But if this thread cannot escape, then the binding will be transmitted. And so the thing that you have is that if your callable creates a thread, virtual or platform thread, using a factory method or new thread, then this thread, the code that is executed in this thread, will not see the binding of your scope value. But because structured task scope is auto-closable and the thread created in a structured task scope cannot escape this try with resource statement, if your runnable creates a structured task scope, then you can't have any loose threads within this context. So the virtual threads created by the structured task scope are going to see the bindings of your scope values. So that's the rule that you need to have in mind. Nothing should go loose. Nothing should escape the scope of this runnable. Nothing should escape the scope of this structured task scope. So if I check the plan, virtual threads were final in 21. Structured concurrency is a preview feature in 25. It will also be a preview feature in 26. And the JEP is already there. If you check the OpenJDK website, you will see the JEP on the structured concurrency 6 preview for 26. It doesn't have a number yet, but it has a draft number that will change to a final number. And scope values are final. And I think I should stop here because my time is up. So the JDK25 is an amazing piece of code. Use it, check it, give feedback on the preview features on the corresponding mailing lists. And if you have questions, I'll very gladly take them. I need to unlock this.
Okay. I think
Yeah.
Jose, because we are all run of time. Yes.
Oh, okay.
Yeah.
Sorry.
So let's big thanks to Jose and thank you
so much.
Yeah, thank you. Thanks for
And
Jose
I'll
for
talk to you
online
soon.
keynote. Thank you.